So imagine that this black dot here in the center is our source of sound. So sound is emanating from it in all 360 directions. We're just going to think about the three-dimensional space. Obviously, what you view is in 2 dimensions. So in 2 dimensions, you see circles, which in 3 dimensions are actual spheres. Yeah? So we know that the intensity falls off as 1 over r squared, which means at a certain distance r, the intensity is the same all the way around at any point on this circle. And then it's the same all the way on this circle, since it just depends on the radius squared. So on a given circle or given sphere, it's going to have the same intensity, right? And intensity is falling out as you go further away from this, okay? So we saw that intensity equals power over area. So that's power, average power, over area, which is the surface area of the sphere, the formula for which is 4 pi r squared, okay? And we call each of these a wavefront. All the circles, the concentric circles, are wavefronts. The arrows, the red arrows outwards, is the actual direction of the wave. Yeah? So the sound wave is traveling in a line outwards, but the waves are spherical. The wavefront is spherical, sorry. So here we're seeing just the forward part in one direction. Okay, so here's the source, and we haven't bothered to show all the sides. We're just looking, for example, at this direction for the wave traveling. Then the wavefronts are spherical wavefronts, okay, all the way through. And they are concentric. Right? Each wavefront is 1 wavelength away from the next. Okay, so that's how we draw them. We draw them 1 wavelength apart. Okay. As you go further and further out from the source, so if you go an infinite distance away, this little portion is going to blow up to have a smaller curvature and a less curvature till it almost looks parallel at infinity, right? It looks almost perpendicular to the ray. So here it is. This is the curvature. This curvature is much less than this curvature. Now, you need to compare similar areas, corresponding areas. And if you go further out, it's going to look almost like a plane wave. So it's going to start looking perpendicular to the direction of motion of my wave. So if my wave is moving along the x-axis, okay, so the wave velocity is parallel to the x-axis, then my wave fronts are perpendicular to it. And they are these plane wave fronts because my source is an infinite distance away, okay? And these are the x and y directions. So remember, each wavefront is 1 wavelength away from the other. You'll be picking up on this concept again in physics too, and dealing with it in terms of light waves.